A very good morning and a warm welcome to the second session of the Professional Development Program organized by BMS School of Architecture in association with the Indian Institute of Architects, Karnataka Chapter. Now, I would like to introduce the speaker of the day, Architect Joy Mondal. He has done his Bachelor's of Architecture from Jadavpur University, Kolkata in the year 2012. He is a founder and director of Research Lab, an organization that excels in design computational consultancy to architecture, to various architecture firms. He's also a visiting faculty at CET and SPA Delhi. Architect Joy has a good research experience in the field of automation of design process and AI. He has also numerous publications to his name, and the most recent one being the Grasshopper plugin for automated column beam placement on orthogonal floor plan. He also goes as a resource person to various schools and colleges, both at national level and international schools. His most noted talks and presentation is the TEDx presented at IIEST in Shivpur. Thank you so much, Architect Joy, for accepting our invite. The platform is all yours. Thank you.
My pleasure. Thank you for the introduction. Good morning, all the attendants. Good morning, all the professors and all my peers. Let me start by sharing my screen. I hope my screen is visible. If you could confirm.
Yeah.
Great, lovely.
Yes, it is visible. Yeah.
Okay. Right, so the topic of this particular presentation is focused on the use of AI in spatial design and analysis. And I deliberately use the word spatial instead of architecture because one of the examples has to do with the urban realm as well. The underlying ideas that go behind developing AI tools or AI methods kind of remain consistent across various scales. So one could also apply them in product design, one could also apply them in other organizational examples in terms of optimizing the organizational workflow, if one is to do that. As my colleague mentioned in my introduction, I head Research Lab and we work as design computation consultants across Southeast Asia. And our job is to provide design computation consultancy to other architectural practices. Most of our work have to do with particular facade design. You may have heard the buzz phrase parametric facade. We kind of delve into that realm. And on top of that, the second most prominent service is that we help practices construct complex double curved surfaces. So we start with rationalizing the surfaces into modular pieces and then generating shop drawings. The third is pretty unique, which is very custom project specific service. Varies from one project to the other. For example, we are involved in the redevelopment of Pragati Maidan in Delhi. In that particular project, our job is to optimize the seating layout of all the auditoriums so that the viewing angle is maximized without any disturbance. All mathematics needs to be coded, which is where we come in. And then there are other projects, but I won't get into that because my focus right now is to deliberate on the use of AI, probably also criticize it in some aspects, right? It has to come with criticism. The outline of the presentation would be that, first of all, I will contextualize AI, draw a few examples from what has already happened, and then talk about where we are in the domain of architecture and design related to how the other industries have developed. The second example would be an example of using AI to interbreed different drawing styles, which is a rather speculative process. The second example would be quantification of the difference between architects and non-architects design reading. How do we perceive originality versus how do non-architects perceive originality? That kind of becomes design analysis, which in a way becomes metadata for us to be cognizant of when we talk about design in the larger domain of public gatherings. The third example would be the use of AI to automate variation of geometry, which is basically an example of iteration. Also, another aspect of use of technology in early stages of design. And the fourth one will be the example of the use of AI to predict the urban safety of different images of urban spaces, which is in the realm of urban analysis, which is why I titled the talk as spatial design instead of architecture or urban design separately. Right. Having said that, let me directly jump into the contextualization. And the story kind of starts in 1997. And in this image, you can definitely see two gentlemen. Is the PDF visible? I am not sure which mode of screen share I select. I guess it's now.
Can you make it full screen?
Yeah, now would it be visible, the PDF?
Yeah.
Yes, the PDF.
Right. Okay, great. Right. So as I mentioned, the story begins in 1997. This is a game of chess. The gentleman on the left goes by the name of Garry Kasparov, the Russian grandmaster at the time. Vishwanathan Anand had a very fabled series of bouts against him in the late 90s and early 2000s. Some of the, including myself, some of the older people in the crowd would remember those, I guess. The fun thing is that the gentleman on the right in the dark suit was not really playing the game against Garry Kasparov. He was simply copying the move that Kasparov was playing and feeding those moves into the system in the background, the black computer. And the computer was deciding which moves to play. The computer, the program that played against Garry Kasparov goes by the name of Deep Blue, which was developed by IBM at the time. In the late 1990s, IBM was kind of the leader of the computation space. And this happened to be the first time when a computer program defeated a chess grandmaster, of course, in the game of chess. And it kind of became a very socio-political news wherein all the articles spoke about human versus machine. Would the future be doomed? Would we head into an apocalypse? Or is the future really going to be rewarding with the use of AI and so on and so forth? But what we need to recognize is that even though at that time it was billed as the triumph of AI over man, the program that played against Kasparov wasn't really AI in its fundamental sense. The AI, by definition of its name, artificial intelligence, should have some level of derivative data extraction or derivative pattern extraction capabilities. What this program did was that by 1997, computers had become fast enough and efficient enough to compute all the possible move sets on a game of chess, or depending on the arrangements of the depending on the arrangement on the chessboard, the system could literally go through all the possible options of playing the next move. So in a way, the program used brute force to quite literally go through all the possible options and pick the one which works best. At the time, it was the most advanced program, so it was called as AI. But these days, algorithms which do not use a higher derivative of logic or intelligence, and instead only search through the search space quite literally one by one, those programs are not called AI. This distinction is important when you delve into more details of what AI is and how AI works. In other words, the umbrella term of AI and what is considered within that keeps on shifting with more and more development of tech. So what may be considered AI right now, probably 20 years down the line may not be considered a part of avant-garde AI discussion. Anyway, jumping 2 decades forward, this board is basically the game of Go, and the people or entities playing this game were the program AlphaGo, developed by Google, and because it's 20 years next, IBM kind of became obsolete. Of course, Google came into the picture, and AlphaGo was playing the game against Lee Sedol, who was one of the best Go players at the time. Now, if you look at the board, you may think that there are white pebbles, there are black pebbles. I mean, why are we replacing chess, such a sophisticated game, with this black and white set of pebbles? But the thing to recognize is that such are the rules of the game of Go, that the number of possible arrangements on the board is greater than the number of atoms in the known observable universe. And this is a staggering fact. It's a staggering stat. The number of arrangements is higher than the number of atoms that we see in the near universe, which basically means that even after 20 years of the initial chess match, even if computers had become exponentially faster, exponentially efficient, they were clearly not fast enough or efficient enough to literally go through those many number of possible move sets, right? And pick one. You can't go through those many number of move sets, which is why Google had to use AI in the real sense and not literally go through all possible move sets. What was done here, and this is fundamental to how AI will in a way affect the design process in the years to come. AlphaGo was trained to mimic human play by attempting to match the moves of expert players that were recorded in videos. In other words, AlphaGo was shown a database of around 30 million movesets of games played between expert human players versus expert human players. AlphaGo was trained to watch a video and extract what is the state of the board, and also extract what is the move being played. And because it had 30 million such examples, it went through the examples again and again and again. And with more and more iterations, it kind of extracted patterns of play. It extracted patterns of play. And what is also important here is that when people are taught a vocation or a skill or a sport, sometimes a senior authority, be it a professor in college, a boss in practice, or a coach in, let's say, in the game of cricket, all of us kind of pass on certain strategies that will make the job easier for the newer guy or the newer girl, right? If we restrict ourselves to cricket, the coach will tell you a certain way in which you have to play the ball, or a certain way in which you have to hold the ball to swing it or spin it, which in terms of computation are basically biases. Through my personal worldly experience and through whatever I have read, combining those two, I have formed a certain strategy, which are basically a certain positive kind of bias, not a negative kind. And I'm passing that positive bias to the next person, and that next person will tinker with it a little bit through his or her own life experience and pass on that modified bias to the next generation. Now, since AlphaGo was not explicitly told or communicated the biases of strategies, and its own job was to extract patterns of play, it extracted certain patterns of play which were not obvious to the human eye. And it ended up playing certain moves which completely surprised the onlookers and Lee Sedol himself. And I mean, Lee Sedol did end up getting defeated, but at the end, in his humility, he mentioned about a particular move that it is not a human move. I've never seen a human play this move. And he ended up saying that it is indeed a beautiful move. Now, this particular, more than Lee Sedol being defeated, this capability of AI to sort of surprise us with new moves or new arrangements is quite crucial, because when enough resources invested into, let's say, investigating how spatial arrangement can be conceived and iterated, then I believe AI has the potential to pop up with arrangements and ways which we have not seen thus far. Ever so often, we do get some seminal work from an architect, which kind of forces us to relook at how space could be arranged. Right? In my opinion, the last such major contribution came from Peter Eisenman when he designed those series of houses in the late 80s and early 90s. I don't suppose anything like that has happened after that. But AI has the potential to propel such conversations. Now, again, this is the last slide to deal with introduction, and then I will jump into direct examples of architecture. And a couple of years later, Google developed AlphaGo 0 instead of AlphaGo. The difference was that, or rather the bottleneck in the previous version was that you can only record a certain number of movesets being played between humans, right? You'll have to arrange n number of tournaments, record the movesets. Some of the movesets are pretty similar to the previous movesets. So you not really, the kind of data being added to the database is not really rich. It's rather redundant. So what Google realized is that instead of training the AI on videos of humans versus humans, or in other words, instead of making the AI mimic humans, what if we teach the rules of the game to this particular AI, AlphaGo 0, and we let it play against itself. Now it started playing against itself now because it did not rely on videos, and it learned from its own moves by keeping score of who's ahead and who's behind and who is eventually winning the game. Kept on bettering its performance, and since it was computer versus computer, the time spent in thinking about a move, physically making your hand pick up a pebble and put it across the board, none of that occurred, or none of that was part of the gameplay, which is why the processing was really fast. And within a span of 3 days, it kind of ended up playing more than 2 billion games against itself. Now here's the fun fact: after just 3 days of training, AlphaGo 0 was made to play the game of Go 100 times against AlphaGo, its predecessor, which played against Lee Sedol. And not surprisingly, AlphaGo 0, the newer version, ended up defeating the previous version by 100-0. And this becomes a paradigm shift, because this kind of demonstrated to the world that we don't necessarily need to take worldly data. If we can teach or encode the rules of the game, then the machine can play against itself and develop its own patterns of play and develop its own tacit knowledge, which basically means that if we have to develop an AI algorithm to generate floor plans, probably we may not need to feed millions of floor plan images or floor plan drawings into the AI system. If we as a community can sit down and articulate how we design, there will be various versions, but even within the various versions, there shall be a common theme. If we can articulate that, then that can be encoded and then fed into an AI system. The challenge is that, unfortunately, it's also positive, but in terms of the computation process, the challenge is that there are certain parts in the design process where we tend to be rather intuitive, and we don't sit down and write down the rationale behind that intuitive decision. And articulating those leap of faith, those little jumps across the intuitive rivulet, those jumps need to be quantified and sort of explained properly by a whole lot of people to arrive at, let's say, a blueprint of steps which can lead us to encode such a process, which can later be fed into the development of AI. Right. So to bring back the examples to where architecture is, I'll give you an example of Frank Gehry's work. In the early 1990s, Frank Gehry was designing the Barcelona Fish and the Guggenheim Museum in Bilbao, both very famous designs. Unfortunately, at that time, the architecture industry did not have software tools which could forget about generating drawings from complex shapes. We didn't even have software which could model and digitally represent complex shapes. Now, Frank Gehry by that time had already kind of become famous, which meant that he had already completed certain world scale projects, which means that he had the resources to go ahead and hire a particular gentleman named Rick Smith, who was an expert of the software CATIA. And CATIA at the time was predominantly used by the aerospace industry and the automobile industry. So aeroplanes have double curved surfaces, vehicles also have double curved surfaces. So the experts in those industries were capable of not only representing complex surfaces, but also deliberating on how those could be constructed. Anyway, so the hiring of Rick Smith led to the use of CATIA, which led to the construction of both Barcelona Fish and Guggenheim Museum in Bilbao. But it was one person from the architecture community with enough resources who went ahead and hired an expert from another industry, an industry which typically pays at least 5x the amount of money that architecture industry would be paying. So it was a very pretty one-off situation, and it took almost 12 years after that for Revit to be released. Now, Revit is kind of parametric, not exactly. I mean, the definition of families arguably is parametric in nature. We can't tend to define the logic in the background, but from the front end, it's kind of parametric in nature. And 5 more years for the first initial version of Grasshopper to be released, which kind of means that it took about 16 years from going from point A of an individual doing something to the first version of a software being released, which could be adopted by architects and professionals in the whole. That I'm hoping that is not the case with the use of AI. Right now, we are in this 1991, 1993 stage in the speculation of how AI and machine learning can be used. But the advantage is that because of internet, because of YouTube tutorials, because of so many blogs and so many workshops that can be done, so many presentations that can be done, for example, this, which would have been difficult in the early 1990s if we were hit by a pandemic at the time because we didn't have internet. Anyway, the process of development is much faster, and I'm really hopeful that it won't take 12 years or 17 years for the first version of an AI-enabled software to be launched for the specific use of architects. Right. Now I will get into the examples and I'll cover 4 of them one by one. Just give me a second. Let me scroll down to that part. Yeah. Right. Now, till about 2018, architects and designers as a whole were kind of skeptical and cynical about the use of AI in the realm of design, because most of the examples being discussed at the time were rather objective. For example, the games being played between humans and machines, like Go and chess and other games. Very objective, right? You have a set of rules, you have a goal, and then you play around with it. Development of self-driving vehicle, again, pretty objective. There's no subjectivity in it. Prediction of stock prices, one of the oldest use of AI and machine learning. Again, pretty objective, no room for subjectivity. And subjectivity plays a very crucial role in the realm of design and art and music and other such things that make us emote. It probably made sense why architects and designers as a whole were kind of skeptical about the use of AI, but that all of that changed in 2018 when Christie's, which happens to be or happened to be at that time one of the leading art auctioning houses based out of London and New York, they sold this particular portrait. It goes by the name of Portrait of Edmond de Bellamy. And if you notice at the bottom right of this particular portrait, it's not signed by an artist, it's signed by, or rather an equation is signed onto the painting. This painting was, as you may have guessed by now, wasn't painted by a particular painter. It was generated by an AI algorithm. And mind it, it was sold for as much as, or rather almost as much as $500,000, which is quite a staggering amount, even in the art world. What the computer scientists did was that they fed 15,000 portraits painted between the 14th century and the 20th century into the AI algorithm. And the algorithm had the capability of extracting certain visual features. For example, texture, where are the edges in your painting? And by edges, I mean where the pixel values change. For example, the collar over here has a clear edge, right? Or the cheek of the face has a clear edge because the background is black, so on and so forth. It was trained to extract edges, texture, and certain visual features. And its job was to learn from those 15,000 portraits and generate new portraits which are not exactly similar to the 15,000 portraits, because then people will kind of label it as a copy or a fake. But at the same time, it should not be so different from the 15,000 portraits that it kind of becomes completely abstract in nature. So a sweet spot needed to be defined, or someone had to control that sweet spot determination, wherein it's close enough to resemble humans, but not close enough to be considered a fake or a copy. And that fine-tuning of where the sweet spot is was controlled by the equation on the bottom right, which is probably why, I mean, I would say it's a very cheeky way of acknowledging the fact that it was made by an AI algorithm. I personally quite like the fact that they signed it with the equation instead of their names. And this event led to a flurry of examples being thrown around, or artists and architects kind of getting their hands dirty in the realm of artificial intelligence. For example, this is some of the work that we did at the time. We basically interpret or used paintings of some of the famous painters from India and tried to see what kind of output could be generated. And it worked with all kinds of mode of painting, different color styles, different textures, something to do with crayon, something to do with watercolor, and it kind of worked with all of them, which led us to sort of formalize this process and try and see how it works when we apply it in the realm of architecture. Now, this process is basically called style transfer. This is the first technical term that I'm using. It's called style transfer, and what it basically does is that it picks up the style and the texture of an example image, for example, this painting of an Italian town, and it applies that on a content image or an, which could also be called as target image. And as you can see, the texture and the color of the style image is kind of flown over the quite basic, straightforward, solid hatch that was used as the content image. So content image in a way provides the geometry on which the style and texture and color of the style image is populated or extrapolated. And it's not restricted to just illustrations. We started experimenting with how it can work with plants. I mean, we all know this is the plan of Ahmedabad Di Gufa by B.V. Doshi, and this is the one on the lower left is the plan of Sabarmati Ashram by Charles Correa. You interbreed the two, one being this being the content, and in the other case, the rectilinear form being the content, we get outputs like this. And if we keep the content image constant and vary the style images, what we realize is kind of astonishing. The AI can automatically pick the visual characteristic style of the style images. For example, from the plan of Ron Shaw, it can pick the angular oblique walls and then apply it on the circular plan. From the one that we've already discussed, it kind of pixelates the circular spaces, and as if to mimic the walls that kind of go along the enclosed spaces, it has introduced certain freestanding walls. Not randomly, mind you. If you look minutely, they're kind of aligned to one of the edges of the pixelated circular spaces. Right, so over here it's kind of horizontally aligned. Over here, if you project it down, it's aligned at this point, which is kind of quite intriguing. And when we talk about a Palladian villa, then it has recognized that the staircase is probably its characteristic feature visually in terms of plan, and it has populated the outside of the spaces with stairs or with steps. If I was asked to add steps around this plan, probably one of the doodles I would sketch would look pretty similar to this. Now, the fact that none of us are explicitly telling the machine that, you know what, this is the trait and we want you to copy this trait. We're not doing that. It's automatically picking up what is the trait and then applying that on plans, which is quite startling, beautiful, and kind of dangerous at the same time, because, you know, give it 2 or 3 years, more people get into the business of this, we fine tune it enough, then we'll have a system where, let's say, we start with bubble diagram, right? We start with bubble diagram, and we from a drop down menu, we pick a style of plan, and then the AI machine will give an output of what kind of a manifestation of that plan for the bubble diagram that we have thought of, or for the spatial arrangement that we have conceived, which will make our job easier in certain cases, probably in projects where the resources are less and we can't afford to spend much time into it. It will make the job easier in those cases, and probably it won't be pretty useful in terms of in the cases of projects which are large scale in nature, because you have so many different rooms. I don't suppose applying styles to those many numbers. If we talk about a hospital, we don't want the rooms to be stylized, right? We want it to be efficient. So probably not so useful in those cases. Right, so if we keep the style image consistent and vary only the way the gradient works in the content image, the output changes from one to the other. As you can see with radial gradient, the way the strokes are applied is different, and when one starts to play around with them, it kind of becomes rather intuitive in nature, and we can kind of start to second guess. And again, we have been using this technique in our presentations, in our mood boards to our clients quite often. We don't have to spend time and energy into sketching something like this. So if I was told to turn this hatch according to this drawing, I don't think I would be able to do a better job than this. And this, mind it takes about 10 minutes to get this output done. I would take much longer, or any expert with. Also keep in mind, we are kind of restricted with medium. Someone is good with oil painting, someone is good with sketching, etc., etc. AI doesn't distinguish like that because it works with pixel values. Again, if this needs to be applied on the hatch, the output we're getting is pretty good. I mean, similarly over here. So It's a question of making the process more accessible, and I'm pretty sure people across the world or architects across the world will start using it regularly. And certain other examples where in the urban realm, if you pick a style image and to try and visualize how a figure ground image would look if it is to be manifested in that style, then we can quickly get an output of the same. It kind of works across various scales, from concept drawings to illustrations to plan to the urban realm, and etc. etc. Now, I did end up, so I wanted to know if the output is indeed acceptable at the human level. And so I am from Calcutta, so I picked up an image of the Howrah Bridge, and I applied a random style image on it. This is the output I got on the right, the enlarged square. And I uploaded this image on my social media account. And to my surprise, none of my friends or none of my relatives had any inclination of the fact that I was not the author of this painting. They had no idea that AI had generated this painting. And of course, they went on to kind of appreciate it. It's kind of makes me nervous about what AI may end up, what the capabilities of AI may end up being, with the amount of fakes that could go around. But yeah, right now the takeaway is that it is able to generate images or able to interbreed plants, which can work as the starting point for further exploration. So we're still 2 or 3 years away from having a very watertight solution, direct takeaway that you mix and match plants and we get error-free representations. That we're still a bit away from that point. Now I will go to the second example. We have about 20-25 minutes left. I'll sort of breeze past them accordingly. Right. The second example is we used AI to quantify and then predict the differences between architects and non-architects' visual perception of originality of design. And in this context, we picked up the tower typology to sort of compare how we perceive originality versus how non-architects perceive originality. Tower typology was picked because that typology, in a way, exemplifies what complex modern architecture is, because kind of it involves expression on the outside with intense level of engineering in the inside. And what led to this study was the fact that there were studies after studies after studies speculating and concluding the fact that facts such as buildings constructed in accordance with the visual code or the elite code of architects is unlikely to receive popular acclaim, which means that non-architects tend to have a whole different set of visual vocabulary than we do. Other studies concluded the fact that architects in general cannot predict the public's aesthetic evaluations of architecture, which is quite startling. I mean, that should not be the case, right? We are in charge of shaping spatial experience of the public. And if we cannot second guess, if we cannot guess what they want or what their preferences are, then we're kind of not doing justice to the process, right? Which kind of led us to ask the question as to what is the, how can we quantify how we look at design and how they look at design? And we began with originality. As an example, we picked up the design of Absolute Towers by Mad Architect. And what we ended up doing was that we made a parametric script with 12 different variables, which could generate iterations of the original design. For example, over here, we see 12 examples of the different variations that were generated. The top right is the original design, and the rest are variations of the same by the use of the 12 set of parameters. Now, the plan itself has certain parameters which gradually morphs the elliptical plan into this star-shaped plan, and then further down with more change, with further change of value of a particular variable, it changes into a rectangular plan. Now, if I go back to the process of how such a study can be conducted, step number one is to produce a whole bunch of design variations or design variants. Then, because we are quantifying differences between architects and non-architects, those design variants have to be evaluated by both architects and non-architects. And with that limited set of evaluation, now, ideally, we should have, with the parametric script, we should have had 10,000, 15,000 different options evaluated, but it's not physically possible to get those many volunteers and get them to rate those many design options, right? Because when we sit down and start to evaluate or compare images, then probably after 100 images, and I'm being optimistic, probably even after 50 images or so, our brain gets tired. So we can't really do it for 15,000 images. Now, this is where neural network comes into the picture. It drastically reduces the number of data points that needs to be collected. So instead of 15,000 data points, probably you can collect 250 data points. There are matrices and thumb rules to decide what that factor of reduction will be. And with this dispersed and discrete data set, which is not intensely populated on the solution space, when a neural network is trained with such a data, it kind of appropriates the solution space. Instead of directly interpolating between them, it appropriates the nature in which the data moves from one example to the other and across dimensions of various scales. Now, pictorially, we can kind of understand this because it involves only two variables, X and Y. But in this particular case, remember that there are 12 variables, which means that the human brain would be, first of all, incapable of even fathoming how interpolation would work. Forget about appropriating the solution space. Now, once the solution space is appropriated to a certain degree of accuracy, then new data points can be extracted from that solution space. And that is when neural network comes into the picture. So let's say the red circles would be 250 in number. And once the training is done, we can extract solutions for the rest of the 15,000 minus 250 data points. So in a way, neural network reduces the effort needed to carry out such studies. Anyway, so like I mentioned, we use 250 design variants. Some of examples are some of which are towards the right, and they were evaluated by 60 architects and 60 non-architects. And we asked a simple question. For each design variant, we kept the original design, which is the top left in this image. We kept the original design right next to each of these variants, and we asked the participants, how would you rate the visual relationship? Do you think the variant is plagiarized? Do you think the variant is similar? Do you think the variant is different? Or do you think the variant is original compared to the original design of the tower? And that led us to certain very interesting results. Floor plan midpoint movement, which is one of the parameters which changes the elliptical plan into a rectangle and into a star-shaped plan, that exhibited the highest correlation with originality. As you can see, positive 0.29 and positive 0.22. Highest correlation with originality for both architects and non-architects. And the second one with the highest correlation with originality for, again, both architects and non-architects is the parameter which controls the size of the plan, or one of the length of the plan. R1 had to do with, I think, width, and R2 had to do with length, or the other way around. I can't quite recall for sure at the moment. Which kind of means that for both architects and non-architects, and this is a commonality, this is not a difference. For both of us, when visually comparing tower variants, both of us tend to focus more on visual features that horizontally control the silhouette of the tower, instead of focusing on lines that go from ground zero to the top of the tower. We tend to focus subliminally, tend to focus more on how the tower is kind of horizontally moving, and therefore how the silhouette is changing along with that. But here comes the interesting fact, which is when we talk about the rotation and between the floor plates, rotation exhibits the highest absolute difference in terms of correlations with regard to originality scores. In other words, none of the other variables have so much of difference between the correlations of architects and non-architects. And it kind of it basically means, the takeaway is that architects tend to be less sensitive about rotation, and non-architects tend to be more sensitive about rotation, but in the opposite way. We don't seem to care much about it, but non-architects seem to think that more is the rotation, less is the originality. Remember, there's a negative sign in the correlation, so they tend to think that it's negatively affecting the originality. The less the rotation, the better, which is absolutely counterintuitive visually, right? Because most towers are extrusions. But you introduce rotation, somehow non-architects tend to think that it's reducing the originality of the example. Probably because the point of reference was the absolute tower, which has a slight rotation. And if you combine both, presence and absence of balcony exhibits the lowest difference between architects and non-architects correlation. So we kind of converge on this. Now, beyond this, if we look at the output, and I'll quickly browse through them now because I have about 15 minutes left. If you look at the percentage distribution of the originality scores after the 15,000 design variants were predicted, if you look at the graph, as we go towards the right, originality increases, and as we go towards the left, plagiarism increases. The obvious takeaway is that architects tend to be more lenient because the graph is more towards the right for architects than non-architects. The peak is more towards the right. You can easily conclude that architects tend to be more lenient at looking at design options as original, which is again completely counterintuitive. We would have thought that probably non-architects, because they're not trained to look at things, would deem it to be more original, but that's not the case. We tend to think of design options as more original. Also, the other fact is that the taller bins of architects is taller than the taller bins of non-architects, which means that there's higher consensus within architects versus consensus within non-architects. And that kind of makes sense because our formal education, regardless of where we've studied, has certain commonalities, whereas non-architects sort of come from a very diverse set of backgrounds. So that takeaway kind of makes sense. Anyway, just to give you a couple of statistics, the average originality score by architects is 27.74% higher than the average originality score by non-architects. Quite a staggering percentage. And not only that, in as many as 92% of the cases of the 15,000 design variants, the originality score of architects was higher than the originality score of non-architects. So it's kind of pretty obvious and pretty straightforward that architects tend to be more lenient than non-architects at seeing design variants as original. Completely counterintuitive, but it is what it is. The data cannot lie. And of course, the use of neural network allows the appropriation of the entire solution space by using a very limited number of survey data samples, like I discussed. All right, now I will go to the third example. Just give me a second and open the slide. This method is called deep isomer, and it deals with automating the variation of geometry to generate iterations, design iterations. And this is a completely fresh out of the oven process. It was done in collaboration of University of Southern California, or at least some of the students from there, about 2 months back. It has not been deployed in any project as of now, because we take a different path. We publish it in paper, in the form of a paper. We get the feedback from the international community, and then we take that to architectural practices instead of rushing the process. All right, what is the deal? You may have seen that people who work with parametric scripts end up making a very long and elaborate parametric script, which kind of then ends up iterating design shapes or design options, right? Now, the challenge to that is twofold. Number one, not everyone is enthusiastic about making parametric rules or learning parameters. And yeah, makes sense. Why would everyone be excited by the same thing? That defies human nature and that defies how society works. The second thing is, even if you are enthusiastic and if you're kind of good at that, you have to define a new logic, a new script, a new algorithm for every new project, because the logic changes from one project to the other. And forget about that. Even in a given project, after a meeting with all the stakeholders, the logic may change after a certain meeting, right? So there's no consistency in terms of logic, which makes sense because that is how architecture should be. It should be customized to the T, but that leads to the problems of people needing to learn the tools to generate iterations. And even for people who have learned the tool, they need to keep revising the scripts again and again and again. Now, our job or our question was, can we use AI to generate variations of a geometry without explicitly drawing or mentioning or writing parametric rules in the form of visual script or hard-written textual script? And the process is called deep isomer because it's kind of a throwback to the phenomenon of isomerism in chemistry, which the best example of which we kind of all know, that for carbon, coal and diamond are the two most famous isomers, right? So the constituent element is the same, but just the way it's structured against itself, we kind of get two completely different forms, and which is basically why it's named deep isomer, because iterating design options is kind of exhibiting isomerism, because the fundamental idea remains the same. The spatial feature and the spatial distribution kind of remains the same, and only the manifestation changes, right? So, which is why we ended up calling it deep isomerism. And the idea was for an AI algorithm to automatically learn the implicit spatial feature from one example 3D geometry. So our job would be to make at least just one, at the bare minimum, one example 3D geometry. AI will learn how the wall is distributed, how a platform is distributed, how the roof is distributed. And once it learns those features, those spatial features, it will start to generate new options. Let's see how that works. There are ready-made algorithms called autoregressive algorithms, which read an image and then they calculate a probability distribution of the pixel values. In other words, let's say if it is to predict, once it has read from a whole bunch of images, while generating a new image similar to those previous images, if it has to predict the color for a particular pixel, then it will go back to the probability distribution of the pixel values of all the other images and kind of interpolate what the value would be for this. Which leads us to certain examples. If you Google autoregressive AI, then you'll find these images as examples, where digits are, which is basically called MNIST dataset. Digits, handwritten digits are kind of fed to this algorithm, and depending on what amount of randomness we select, it spits out different kinds of for auto handwritten examples. For example, this one is a clear 5. Some of them are too complicated to be legible as a digit. So it kind of depends on what kind of randomness we're introducing to the system. Now, in terms of 3D, I won't get into much details of the technical aspect because that is not the aim. The aim is for me to present, let's say, a bouquet of ideas. Right. So in terms of 3D, our challenge was to translate a 3D geometry into an image, because the image to image variation and generation algorithm exists, as I mentioned. So how can we translate a geometry into an image with relevant geometrical or spatial data? Then once the variant images are generated, take those variant images and regenerate the corresponding 3D geometries. That was the fundamental challenge once we figured out how the image to variant images were generated. Now, the solution to this, in my opinion, is pretty interesting. Step number 1 is that we overlay a grid or underlay a grid onto our example geometry. So the right side has the grid underlaid. And once the grid is underlaid, we can extract the grid cells that are unique. And the image on the right showcases all the grid cells that are unique, which also means that when these unique grid cells are repeated by a certain number and repeated in a certain pattern, we will get the geometry on the left, right? So we're talking about two things: number of repetitions and where they're repeated, which is an abstract way of talking about pattern making. So pattern of numbers, pattern of placements, or pattern of numbers and pattern of locations. And AI is really good at detecting patterns. Similarly, if once we know or calculate the number of repetitions, let's say this particular cell needs to undertake to generate this, and we slightly tinker the location instead of changing the number of placements, it will generate a similar yet different iteration, right? So depending on where the unique cells are placed and depending on what is the volume of the unique cells, what is the area of the unique cells, we translate it from 0 to 255 pixel values, and the image on the right becomes a pictorial representation of the 3D geometry. Now, for example, the lower left corner is empty, which makes sense because even here the lower left corner is empty. And right after the lower left corner, we have a freestanding wall which goes from the left to the right, which is kind of represented here as well through this dark line. Now, the leftmost pixel of that freestanding wall is lighter than this. Why is that? Because if you look closely enough, the leftmost pixel or the leftmost cell has only half of it occupied by the freestanding wall. And as I mentioned, it is the blackness of the output image in this case is dependent on the area and the volume of the geometry on that particular cell. More the surface, darker will be the color. Anyway, so this is fed into the system and it starts generating and spitting out design variants. As you can see, continues the freestanding walls and sort of has different kind of the same data is kind of pasted across the rest of the spaces. Now, what AI needs to do is that it needs to undertake a lot of iterations to learn the spatial distribution. And once it goes through enough number of iterations, it is ready to spit out options which are legible, which are meaningful. Otherwise, we'll end up having options which are not meaningful. For example, after only 1,000 iterations, we end up getting options which are kind of gibberish in nature, but at the same time, we can kind of see that patterns are emerging. For example, some of the options have certain patches of the freestanding wall. Some of the options have certain patches of the platform at the ground level. Yet, it has yet not learned the spatial distribution to the extent of our satisfaction. Now, when we pushed the number of iterations to 1,000 iterations, it started producing absolutely perfect results, which is quite astounding. Remember, if I am to parametrically define this as a rule, I'll have to say, make a freestanding wall, make 2 of them go all across, make 2 of them go only half across, make sure that the ground platform is watertight to the freestanding walls, make sure that the roof shading is watertight to the freestanding walls, etc. and etc. We are not doing any of that here. It's simply generating a pictorial representation of this. AI is converting it to variants after enough number of iterations, of course, and those variants are then re-represented or translated back to its 3D form. And as you can see, platforms are watertight, roofs are watertight, and of course, the number of freestanding walls in different directions, be it continuous or split or half, or the ones that don't go all the way across, it's the same. And it's quite astounding because I'm not mentioning any rule. All I need to do is give an example, wait for the AI to work for about half an hour, and it will give me as many options as I want. It's kind of seems quite utopian at the moment. I'm really hopeful that we will be able to send it out in as an open source freeware solution for architects. Our aim is to make it an installable plugin for SketchUp as well as Rhino, where you make a model and you click 5 or 6 different buttons, as in how we develop the UI, and then you'll be able to automate your design options. And it's not only restricted to just one input geometry. We can refer multiple input geometries, and it will learn the spatial distribution of all the input geometries and then produce output, which is kind of an interpolation of all of them. So different kind of output can be speculated with such an approach. Right now, all the examples are orthogonal in nature. We have not tried this with curvilinear shapes or absolutely freeform shapes. And we quite honestly don't intend to do that at this moment. We want to ship this out as a free plugin, get the feedback, if it is useful, if people are saying that they want the curvilinear shapes and freeform shapes to be incorporated as well, then we're going to spend those many extra days and those many extra weeks into figuring that out. We don't want to jump into all the different threads of geometries right away. But yeah, the takeaway is that gradually we are arriving at a stage where we won't have to explicitly mention the rules, and AI will kind of take care of the process of iteration. And we will have more time to think of the initial example. We will have more time to think of creativity and the mundane things of tweaking geometry and making iterations, etc. Those will be kind of passed on to AI. And all we have to do is take the executive decision of picking the option that works best for us. Could I have 5 more minutes? I'll go through one last example.
Yeah, yes, sir, you can have. Yeah.
All right, thank you. Just give me a second. I'll share the last. Right. The last one is a website that we're developing, which is going to be called Safe or Not. And our aim is to take it to different municipal corporations to run safety audit of the major Indian cities. The question is that, can we predict the safety of cityscapes? When we talk in terms of safety, most of the discussion is related to active measures, and rightfully so. And by that I mean installation of light at night time makes sense. Increase of patrolling makes sense. Fast redressal of complaints makes sense. And the large-scale strategy of sensitizing both men and women from the time they're kids through subjects related to gender studies and individual rights and public safety in the school curriculum. All of them make sense. But often what is kind of ignored is the fact that quite literally architecture, and by extension the urban fabric, kind of plays as the canvas on which all of these things happen, right? So how I will feel when I walk into an unknown narrow alley, how safe I'll feel, that will be very different from how safe I'll feel if I'm walking next to a highway versus I'm walking next to a market versus I'm walking along let's say a neighborhood that I know of. Our perception of safety will be so very different. And it's not just me, every person will have different variation of how safe he or she will feel. And our job is to quantify that. The process is kind of similar to the originality exercise between architects and non-architects. So I won't get into much detail. I'll just give you a brief idea. And the idea is to, at the end, when Safe or Not will be developed into a website. Right now, it's all clickable and executable on our end through scripts. We have to now figure out how we can translate that into a website, but that process is ongoing. What we'll end up doing is that the user will be able to upload images, and from the images, the algorithm will quantify, let's say, what percentage of the image belongs to which object type, what percentage is sky, what percentage is building, what percentage is vehicle, what percentage is human, so on and so forth. And depending on the data that is already collected, and depending on what is the percentage distribution, it will give us what is the predicted safety score of that cityscape image. And for, of course, different spaces will have different predicted safety score. Now, right now, what we've done is that we are kind of aggressively pushing towards collecting data to make the algorithm more and more accurate. when this presentation was made, we had around 1,000 images rated by willing volunteers. But right now we have about 2,000 images that have been rated. I am hoping that we'll get 5,000 images rated by the end of the year, after which we can start translating it into the form of a website. Anyway, the underlying idea is this. With the bunch of images of cityscapes, there are pre-existing machine vision algorithms which can, in a way, extract what are the object types in those images. For example, if you look at the image on the left and the image on the right, the vehicles are colored blue, humans are colored red, tree crowns are colored green, sky is colored blue, and buildings are colored gray. And this semantic segmentation algorithm divides any image into these 19 different pixel percentage scores. As I said, what percentage belongs to road, what percentage belongs to traffic signal, sidewalk, etc. and etc. Basically, the compositional elements which we see when we walk around a city or walk across a city. And it kind of makes sense because our brain intuitively sees the number of vehicles and the number of people and the sort of the distance between the buildings, and therefore what percentage of our view is covered by buildings. And then it kind of intuitively decides how are we feeling about that space, right? And so this algorithm is a direct throwback to that particular example. And I'll just give you an example of where this is from. I'm hoping that you can see this video. The algorithm, which divides it into different constituent elements, was developed by MIT when it was in collaboration with Uber to develop self-driving vehicle algorithms. And of course, when a vehicle has to navigate a city or a street, it has to look at its environment and figure out where are people, where are traffic signals, where are trees, where are buildings, where does my road end, where are sidewalks, so that it doesn't hit those and it can safely navigate where are the other vehicles. Now, videos are basically a series of images, right? You increase the FPS beyond 30, it kind of stitches them smoothly and our brain can't detect the difference between images and video. Now, what this being applied on video can, of course, also be applied on images, and that is exactly what we have been doing. This was developed with an open source license, so we don't really end up getting into the realm of intellectual property rights. They are generous to make this open to all. And on the other hand, we have the subjective evaluation scores of how the participants of the survey are labeling the images. Is it very safe? Is it very unsafe? Are you unsure? And then there are 9 different categories and gradations of them. So the input values become the features, the output values become the safety score, and then a neural network is being trained to interpolate or to map the data of the input values to the output value. And once that mapping is done with enough number of images, the accuracy will be ramped up to an extent where any new image can be accounted for. And that is our aim by the end of the year. After that, what we'll do is that we are going to collaborate with different municipal authorities to run safety audit checks of different neighborhoods. Our aim is to get some sort of a grant to get vehicles move around different streets of a city, or if not the entire city, start with a certain block or a certain neighborhood, make it move around the street and click pictures, right? And then have those pictures marked with the GPS coordinates. And for each GPS coordinate, there would be a picture, and we're going to run that picture through the safe or not program. It will give us a safety score, which basically means that for all the GPS points of the neighborhood or the city, we'll have a safety audit map where we can visualize it in different ways with heat map visualizations or spike map visualizations, so on and so forth, right? It will help us identifying areas which are safe or which are unsafe. And the last slide, right now, the initial analysis tells us that higher the amount of sky, the safer we feel. Higher the amount of sidewalk, the safer we feel. The higher the amount of traffic signs, the safer we feel. And on the other hand, the culprit seems to be motorcycles. Higher the number of motorcycles we see, the more unsafe we tend to feel, which makes sense because we all end up seeing a lot of accidents, motorcycle accidents, right? And the kind of two-wheelers are kind of notorious about changing lanes, getting onto the footpath, and then running havoc to cut corners. Right, with that, I am going to conclude my presentation. So this kind of changes the way the process happens. We, through data collection and AI experts, will not suggest what should be the right way or what is safe or unsafe. The data is explicitly coming from users, and that kind of makes the participatory process quite literal in nature, where we don't make a design, take it to the public and take their feedback. The starting point itself has some information or feedback through data collection and the use of AI. Right, over to you, Ranjan, and I'll be happy to take questions.
Yes, we do have questions. Shubhadra, you can unmute yourself.
Hi.
The question.
Hello, hi, how are you doing?
Good. Had a small question. Actually, it is a very basic kind of a question. Just wanted to know your opinion on how AI is going to make this whole parametric architecture more humane, because most of the time what's happening is parametric architecture is turning into a very visual kind of an architecture. I mean, and a lot of criticism on why it is not very social, I want to say, and it doesn't take a lot of social constraints into consideration. Those are some of the accusations into architecture. Ironically, getting AI into parametrism, what's your opinion on how it can make it more humane?
Right. There are two threads through which I would like to address that question. Thank you for the question. Parametricism has gotten a bad rap, unfortunately, due to Patrick Schumacher, who works at Zahadir Architects. He is very aggressive in terms of labeling it as a style, which is why you see blobs and double curved surfaces. But at the core of it, parametricism is an approach of how you define a system. Even a cuboid building is parametric in nature if you change the length, the width, and the height, and the orientation at which you place that cuboid on the side. It becomes more obvious when you read about what parametricism means in engineering disciplines. They don't talk about the final shape. The final shape is the manifestation of a parametric system. So the bad rap that parametricism has received, I will say that it is down to us as architects, because we have failed to recognize what it actually means, and we've kind of fallen into the trap of Patrick Schumacher in terms of celebrating it as a style. So Rhino releases a new freeform modeling command, and we kind of take it up without really rationalizing why it is to be taken up. Now, it is a challenge to incorporate social objectives in digital models, not just in Rhino, Grasshopper, or any parametric tool, but even when we're sketching or doodling, it's the representing the intangible into a tangible sketch is very difficult. I would say quite impossible. That has to, unfortunately, still, even with the use of AI, depend on the sensitivity of the designer. At the end, AI will be able to generate thousands of options. But if I am not sensitive enough to pick the right option, regardless of how good the AI is, the design will be useless. So we'll always have to fall back upon the tacit knowledge that we gather through our rigorous education and practice. And AI at the end will augment the process, will make the process faster, which means that we'll be able to cater to more people and be able to have more clients. That's my take on it. But lastly, I would like to add AI and parametricism are very different in the sense that AI is used for problems for which we don't know the process or for which we don't know the algorithm. So we have an input data set and the example output, and we don't know how to map those two, which is where AI comes into the picture. Whereas in parametricism or regular computation, it's the other way around. We know the process. We know we want to square and then we want to extrude it and then we want to reduce another square from it, etc., etc. So when the process is known, it delves into the parametric realm. When the process is not known, but we have many real world data examples, then we get into the business of AI. In my opinion, AI will be more accepted by architects because it has not been hijacked yet by someone like Patrick Schumacher to represent a particular style. And it's more analytical, which is one of the foundational tenets of the process of design. Yeah.
Thank you.
Thank you.
Joy, I have a question.
Sure,
First of all, very nice, informative session, very useful session and need of an hour, I should say. And a few of the slides where I could guess that, the most of the preliminary surveys, where the physical surveys can be eliminated by using these kind of software. Okay, so my question is here, like in one of the slides you mentioned about the style transfer, where you have used the content image and then the style image and went for the target image. So you have used in the style image, you have used one as an alternative. So can you use 2 or 3 alternatives and get the output image? And if yes, then what will be the kind of a copyright issues which you will be dealing with, like once you get that the extracted image from these kind of a combinations?
Yes. Thank you for the question, ma'am. I did want to touch upon that. You can have multiple style images and it will kind of interpolate the different styles into that particular target image. As far as copyright is concerned, because the process is so new, the legal system is yet to catch up with it. So I quite honestly do not know what the answer to it is. Also, it's honestly beyond my paycheck because I don't know the intricacies of copyright laws of images. I know about what happens with 3D shapes. We've had this famous example of a student suing one of the American architects about 7 or 8 years back because he alleged that his studio design was copied by the architect who had come for the jury. And you kind of know about that, but I'm not sure about what happens with images. The safe bet is to use reference images as input, which are open source in nature, which can be used under CC license instead of blindly downloading images. Also, the copyright issue has a philosophical bent to it. Is the person who is making the AI do it the owner? Is the AI the owner? Or the individual images taken from the individual authors the owner? Or all of them are owners in certain percentages? That's a philosophical question which needs to be discussed. My estimation, my idea, because I kind of think about equity at times, my idea, I would go for distribution of ownership and not at least acknowledgement of the contribution, if not explicit distribution of ownership.
Yeah, thank you. I have 2 more questions. Another one is like during my research, I have used ANN as a software, artificial neural network as a software, to find the gap, missing data between the, like electrical points or, the water meter or something. Some reading was, there was a missing data. So during that time, I have used ANN. So is it, again, the software works in a similar line, what you have explained in artificial intelligence? So that's the question.
Yeah. Yes, ma'am. The fundamental idea is similar, but the building blocks of the internal process is obviously different from one process to the other. The fundamental idea, when you were appropriating the missing data point, it was basically extrapolating the existing data points and bridging that gap.
Yeah.
Here, the same thing happens, except the process is slightly different. It kind of deals with neurons and weightages and activation functions and a whole lot of mathematical mumbo jumbo, which I'm not getting into at the moment.
Okay, the one last question is like, what are the challenges in predicting human behavioral pattern? You know, like especially in terms of when you analyze the data based on the present circulation and you predict something like, you know, in future, in especially in public spaces, you know, like in and around maybe some metro or maybe in island, busy islands and all that. When you take that data and then when you predict you using this AI and ML, and when you say, okay, this is going to be you know, the future kind of predictions, but how real it will be, because human behavior is something which is really challenging one. And then how do you face these kind of issues?
Yes, ma'am. That is a challenge faced by industries across the world. The word I would like to use is fickle. We tend to be fickle in our behavior.
Yeah.
And one of the primary challenges being faced by traditional AI companies is the fact that we are not consistent in saying the same thing, or we are not consistent in talking about an objective event later on. Forget about asking me about a certain event with a gap of a week. Even if you ask me in the morning, what I'll say will be different from what I'll say in the evening.
Because all mood swings and, you know, the timing, there are so many influential factors which may not be constant. Even the climate, even, you know, the surrounding and everything matters for that.
Yes, ma'am. So the answer to that lies in the step of data collection. We have to collect at least certain percentage of data divided across all the possible set of scenarios. So for example, the safe or not data set is exclusively developed with daytime images, because the algorithms are yet to work well with nighttime images, because the amount of pixel value difference is less in nighttime images, right? Which is also why our eyes find it difficult to distinguish between objects at nighttime. So if there are algorithms, then we'll have to have a separate set of data set for daytime, dawn and dusk, and absolute darkness, and also artificially lit up public space. So that data space, and also we are also collecting data for different genders. Right now, it's not presented as such because we need more data and we're doing it. So one may say that, okay, we'll do it for men and women, but then there's something beyond the bi-gender spectrum as well. So even that data needs to be collected. Data collection is essentially 70% of the process of developing any AI algorithm. And the question becomes, from where do I source data for people who don't identify as men or women? If I explicitly go and seek those people, then I introduce a bias in the data collection process.
Yeah.
How do we navigate through that process? It's always an estimation that kind of have to do a cost benefit analysis and try and see what works best. But my answer would be that the data collection needs to be as comprehensive, as composite, and as diverse as possible. That would probably mask any irregularities.
Thank you, John. Thank you.
Thank you, ma'am, for the questions.
Bhavesh, the next question is from Bhavesh Kumar.
Yeah. Hello. Hi. Yeah. Hi, Joy. So it was very interesting presentation and really eye-opener. And I think this is definitely influencing all of us to think differently. So I just have two questions. Already one question is you have answered, like, what are the human aspects I consider, because as Ian Gale is mentioning, we must design for people. So my second question is like any socio-cultural aspects that how would you collect the data? You just mentioned that this AI system works based on a large data collection and then it will be processed. So how would you put this one, the socio-cultural aspect, like if you work in Africa or if you work in China or, where there is a very sensitive culture. So.
Yes, thank you for the question. Translating subjective and qualitative phenomenons and data into a quantified and objective version has been a challenge throughout the history of statistics, right? So to that regard, whenever we translate something qualitative and subjective into objective, there will always be a certain data loss in terms of quality. That is a given. Now, I'll go back to the simple the example of safe or not. If it is to be sensitized to different regions, then a whole set of data needs to be collected in that region. So if I'm doing it in India, then the same set of images need to be rated by people from China, and that will sensitize the AI for China. Or in other words, there needs to be an additional column in the data set, which sort of tabulates the region from which the person is, the gender which the person identifies with, let's say the ethnicity of the person, the language of the person. The same way census works, if in ideal terms, if we collect those labels as well, and we have enough data, then the AI algorithm will be sensitized to that. Because for every new algorithm, so if me as a human become a data point, so I'm male, I'm from Bengal, I'm Indian, so because those data points will already be in the input data set on which the algorithm has learned, the output will be catered to my condition. And it is a challenge because most of the AI developments are being done in the West, and specifically being done by straight white males, which is why you may have come across articles which say that when detecting potential crime or when using facial recognition, Black men are typically considered to be potentially criminal more than white men. And so there are these racial divides. Certain facial recognition algorithms are not even able to recognize Indian faces. Even, for example, when they came up with Siri or Alexa, the first two iteration could not recognize the way we speak English, if you remember, right? So then they had to train the algorithm with the kind of English we speak, and then the algorithm got sensitized to us.
Right.
So
yeah, it's pretty challenging, and I think it has to be contextual. But yeah, my just last question is like, what do you think, in your opinion, that in case if we adopt this AI system into practice, how it will change our thinking, the future thinking, how it can have an impact? Because definitely it has to consider all these aspects. But once we start, that maybe our thinking may change.
Yes, the first impact that I see is in the fact that in the realm of collaboration, it will become easier between the architect and the client, or the urban designer and the people who live in the neighborhood. For example, if I am designing an intervention in a particular locality, I'm going to give an app to the users or to the residents of that locality and tell them to upload images or click images that they visually like of a cityscape, and upload images or click photos which they don't like, which visually. And then I'll crunch the numbers to determine their aesthetic sensibilities, as an example. Now, the same process, if I'm, instead of doing it in Delhi, if I do it in, let's say, Bangalore, just by virtue of different people staying there and them having different sensibilities, the data that I'll end up crunching from their uploaded images will be different. So the participatory information will become way more customized once these tools are deployed in real world projects. As far as architecture is concerned, more of the processes which are repetitive in nature will gradually be eliminated. For example, like I mentioned, I lay down a series of space in a certain graph connection, as in with certain node connections, and then we'll end up having an algorithm which will manifest it in different geometrical forms. we won't have to sit and sketch it and then modify it. The initial options will be given to us, and then we can tinker around at the micro level or at the local level.
I think this can be useful to housing sector very much, perhaps also.
Yes,
By
yes,
knowing the current typologies, because it seems no developer has done any research that what sort of work from home, or let's say small apartment, or cost, all these parameters. So that's what I think it'd be tremendously, I think, helpful.
yes. And I'm hopeful of the fact that many graduates right now are going to the West to study such subjects. They'll bring back their knowledge, and we'll have more examples of this across India as well. So for example, about 10-15 years back, a lot of the graduates when they went to study in the West, they learned about parametric design, which is why we have a fair share of parametric design going on in India as well, at least in the major discussions or the major avenues. In about few years' time, I'm pretty sure AI will also become one of the major talking points. And I think AI will do what parametricism hasn't been able to do, which is make the process more acceptable to a majority of the architects, just by virtue of the kind of problems it tries to solve. Parametricism has been dogmatized to solving aesthetic questions. That is only but 1 to 5% of architecture intention, right? But AI, by definition of how it works, you will have to apply it to problems which are not aesthetic in nature, because AI doesn't solve aesthetic problems. So I think it'll be more readily accepted in the industry.
Yeah, I think it will be helpful to solve the problems, and then we may think about the dreams. So perhaps it will give us more time to think about dreams, which was the original idea of cities.
Yes.
Yeah,
Yes.
and not like solving the traffic problem or waste disposal and all these other problems. We are now busy with so many problems because we have created them.
Yes, yes, I absolutely agree with that.
So I think it will be definitely, I think, useful, and it will, I think, change the way we think also.
Yes, yes.
Yeah. Thank you. Yeah.
Thank you.
Yeah. Thank you. We are going to stop the question answer session due to the time constraints. Architect Joy, I personally am a bit spooked by the whole presentation of how the AI sort of develops. But at the same time, I definitely don't want to sound like my grandfather, when he heard of computers for the first time. So I think as an urban designer, there's quite a lot. I personally, because there's a lot of the data points that are there, and we as a human being, we tend to miss out, and AI sort of captures all of it. So that was indeed a great session, and it also opened up doors to imagine space from a whole new perspective. AI to most of us is a new area. Thank you so much for throwing light on this, Architect Joy. Thank you. Have a great day.
My pleasure. My pleasure. Thank you for having me.
Yeah.
Have a good day. Bye-bye.
Yeah.